Okay, I'm set on this one too. As I mentioned last time, I've been tinkering around in GIS for a number of years. And if you do come to the next in the series, I'll suggest that I was doing GIS in 1954. We're going to have to talk about that because we really didn't have computers then. But I've been at it for a long time, most certainly since 1974. So that's 40 years. So the next discussion, I'm going to try to relate to you some of the scar tissue, some of the success possibilities, some of the things we encountered in that 40-year time slice that I'll say is the most radical, the most evolutionary period in mapping. 40 years, and we went from paper to digital. And a digital map is radically different than a paper map, as we'll even see today. So the premise for today: while natural resources and agriculture have significant differences in their respective motivations, goals, decision environments, and technological approaches, advanced map analysis and GIS modeling applications are bridging these differences. So I hope to get across today is how agriculture and natural resources, it's paradoxical. They were so far apart at the start. Totally different mindsets as to what this discipline was, what GIS was. And by now, I think they're starting to meld their minds. So that's going to be what we play around with. A little bit of review from the last time, for those that were here last time, is that we have this thing called geotechnology, and it's on par as one of the mega technologies for the 21st century with nanotechnology and biotechnology. There are only 3 mega technologies for an entire century, they say, and we happen to be one of them. And it started off in the 50s, yeah, you could argue 40s for remote sensing. Global positioning came on board in the military kind of in the 70s. Civilians in the 90s. And this geographic information systems, at least the word was coined in the late 70s. Pretty new technologies. And that spatial triad of GPS, GIS, and remote sensing, if you look at the GIS portion, it kind of bifurcates. There's a mapping charge, that's what it does. It maps and analyzes, so there's a mapping side. And I like to refer to that as a technological tool. And primarily there are 3 large areas. There's the mapping itself, automated cartography. Could we move maps onto the computer? And then there's display. There's a lot of advantages of a digital map display over printer paper display. And finally, geoquery was the biggest input part. That idea that you can search and find certain classifications that you're looking for of groupings of maps. All right, so that's the mapping side. So on the analytic side, when we say, yeah, but it's also an analytic tool, we're kind of looking at maps as numbers, organized sets of numbers. Just like matrix algebra has organized sets of numbers you can do certain things to. Well, there's certain things we can do when we analyze maps as numbers instead of pictures. Starts off with 200-year-old science of mathematics, spatial mathematics. All those mathematical formulas that support making maps. We had to have Descartes and a few of the other mappers, and even before them, to come up with the equations that dealt with a round globe and a flat map that you could put in your pocket, for example. So those are what I'll call spatial mathematics. The 2 we're going to play around with: spatial analysis investigates the contextual relationships within and among mapped data. And spatial statistics investigates the numerical relationships within a map and among maps that are organized sets of numbers. All right, that was a little bit of review. Here's kind of the closeout on that intro review. We have this remote sensing, GPS, GIS, the triad, the spatial triad. And if we think about GIS, its history has been as a discrete rendition of geographic space. And that means we're going to deal with spatial objects, points, lines, and polygons. And they're globs. Everything within a polygon is considered to be uniform. And it is because we classified it. We said this is Douglas first timber stand. Well, I bet you there's a smattering of aspen maybe in there. Maybe some spruce moved in. No. We'll assign it to what is dominant. Well, that's way different than what we do on the raster side. In that case, we treat space not as a set of irregular spatial objects in space, but within an analysis frame. We stick a grid pattern over it, and this is actually what we did in the 70s, if you had to take a course from me in the 70s, is we take an acetate grid, we'd lay it over an air photo or a map. One student would sit there with their little finger on it, and as they went across a row of those little squares, they would yell, Doug Fir. More often they would yell 1, maybe that was vegetation type 1. And someone sitting at a key punch machine would go 1, move over, 1, Doug Fir again, 1, aha, 2, ponderosa pine. We literally, that's the way we digitized in the 70s. Well, there's a digitization. Everywhere you see a 1 is open water, everywhere you see a 2 is a meadow, and everywhere you see a 3 is classified as forest. The analysis frame is the partitioning into the grid cells. In today's world, your choice. Do you want them to be itty bitty little tiny cells? Or should they be big cells because I'm doing a big project to cover the whole state? In mathematics terms, that's called a matrix. They love matrices. The computer loves matrices. Everybody loves matrices. What they don't like are proprietary topology sitting behind every one of the different systems. That is generalizing geographic space in homogeneous areas. It's just not nature. Well, if we have this analysis frame, and if we fill those little squares with numbers, we have what's referred to as a map stack. So I don't have to say point in polygon, line cross polygon, polygon intersect polygon. I don't have to do any of that kind of stuff. I just go to one of the squares and say, what is it on the first map? What is it on the second map? What is it on the third map? And that's a database query that is lightning fast in the computer. Also, all topology is in the grid. It's all implicit. There is no explicit topology. Ooh, who's on my right? Who's on my left? Well, there's a cell on my right and there's a cell on my left. Go find out what's there. How far away are you? 1, 2, 3, 4, 5, 6, 7. I'm 10 cells away. All information for the computer to analyze is in the analysis frame. That's how come we can do analysis, sophisticated analysis. Well, what's that involve? Raster data. Who don't like it? That's disgusting. Most cartographers would say that. Disgusting little squares. Every time you look at this, say, screen up here, you're looking at little squares or little dots. That's raster. And it can make a pretty fine looking map. So maybe in the old days there were big squares, but not today. And our data needs to be disaggregated. That says we're going to deal with the continuum of variability in space. We're not going to precondition and put it into these spatial objects. And finally, the numbers that we represent things with. Quantitative. Opens up all mathematics. You can do anything you want to that set of numbers. Quantitative, you can do a lot of things, but not quite as many. So we love to have our numbers be ratio quantitative. And if we do that, it bifurcates into two general arenas of analysis, map analysis. One is spatial analysis operations, and the other is spatial statistics. Here's an example. ArcGIS has a grid-based analytic module called Spatial Analyst. It has 170 individual tools organized, as you see. And unless you're an ArcGISer, you don't quite understand that organization very well. So my charge over the last about 3 years is translating all of those capabilities, all those mathematical capabilities, into something I like to call spatial STEM, because it speaks to the science, technology, engineering, and math language that's common among all those disciplines. It's a mathematical framework. All right, that was our review. How about we look at this thing from an application perspective? Mathematical framework is kind of where natural resource sits. A lot of what they do analytically with maps has to do with the relative positioning, terrain analysis, variable width buffers, emergency response, we'll look at a couple of those, visual exposure, shape pattern relationships on the landscape. All of those are kind of dealing with the spatial arrangement of numbers in space. Where if we go over to the other side, spatial statistics, it's not looking at the context as much as it's looking at the numerical relationships among those numbers. You know, that's where precision ag came from. Actually, they love their navigation, and they love their yield mapping. But then they also build nutrient surfaces. They deal with dependent map variables and independent map variables. And they do a whole lot of science. Statistical analysis. And it has a lot to do, as we'll see, with the spatial coincidence. For this square, how much phosphorus is there? How much nitrogen is there? What's the pH? Potassium there? Organic matter? And then I'll, just like it was a little field I owned, you know, maybe a 6 foot by 6 foot field, 5 foot by 5 foot, how would I manage that field different than the next field over? Site-specific management. That's where they showed up to this technology. See the difference? Natural resources, my great-grandfather in forestry, didn't call it forestry then, it was just kind of whacking down trees, but you know, they knew maps were important because it was an inventory of their resource, what they bought. So there is a legacy, a paper map legacy behind natural resources, the inventory side, not in agriculture. They weren't inventorying in space. So they said, well, there's some of this new fancy science stuff, and you know, agricultural science is really into statistics. They say, well, maybe we can express that spatially. All right, we're going to play that up a bit. But before we do, another little bit of review. And if we come down here, see if this works.
Okay, and roll in on this.
This lecture from last time does sit on the internet.
And I've been around.
You know, I don't want to close it. Yeah, I guess I do want to close it. So for those that weren't here, those that couldn't remember what the heck happened here, want to review it, it's sitting out there on the internet at this location. And Sophia knows that location, maybe spread it around. Otherwise, I'm going to give you a quick review. We've got a mathematics. So I tried to draw. Oh, it's tough to do. Friday, freely, late in the afternoon, that there's such a thing as a spatial derivative. We have for several hundred years had this concept in math called a derivative in calculus. Well, there's a spatial derivative, and it, for us, it's slope. But it doesn't have to be dirt. It can be abstract surfaces we're going to talk about. What do you think the first derivative of a barometric pressure surface over Colorado is? Derivative, slope, slope. Rate of change in the z over the rate of change in xy, called the run, called the rise. So what would happen if the barometric change in a little bit of space is really great? What happens? Your children are going to ask you this. Explain why there's wind. Barometric pressure differences. And when those differences are close, steep, you have really high winds. And when they're far apart, you have gentle winds. And when the barometric pressure is the same, you don't have any wind at all. So what do you think the direction of the three-dimensional first derivative of a barometric surface would be? This is GIS. At least it's tomorrow's GIS and not today. The direction of the wind. We've been doing that since 1950 to build Rose diagrams. You might have seen them, they're arrows. If it's a big, long arrow, it's a strong wind. And the direction is like the aspect on a terrain surface. Tells you which way the wind is blowing. 1950, we're doing that by hand. Now it's all done on the computer by taking the first derivative of a barometric surface. All right, let's try the next one that says, there's this advanced math. And in that little example, as I took the cosine of dirty terrain slope, multiplied it times the planimetric area of the sill, and it calculates the slope area. Because when you tilt up the hill, there's more surface area than planimetric. I don't know anyone who doesn't report acreages just based on planimetric. Try doing that in the San Juans. I mean, you'll be understating the acreage of that property that you could run cattle on, by 60% probably. But it's just part of our, we never did it with a paper map. Why would we do it here? That's disgusting, don't do that. All right, let's try this last one. The spatial integral. Well, integral is the area under the curve in mathematics. But over here, we talk about summaries under certain, I like to call it a template map, a cookie cutter map. You lay it down on another map, in this case elevation, and I could compute the average elevation. I could compute the coefficient of the elevation within there. I could calculate the number of deer population in there. It's our summary tool, zonal, our zonal summary tool, that we've had since the 70s. Every GISer should be out there using this stuff. All right, then we went off and said, there was even more exciting things happening. Distance. We went from the idea of Pythagoras and the ruler that was dictating to us that everything moves in the shortest straight line between 2 points. That's pretty darn limiting because nothing, and I mean nothing, moves in a straight line. So you're making some errors there when you decide everything moves in a straight line. So introduce this idea of a splash technique. A rock falls in the water, one away, two away, three away, and it's like nailing and spinning the ruler. Well, that all of us says from a point to everywhere. Or from a set of points, splash, 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 splash. Every house, proximity to house map. Then we said, well, why don't we relax that idea that everything has to be straight? Because I don't drive my truck in a straight line. I'm constrained to the road network. And then as I move off the roads, I'm constrained by whatever movement I'm taking there. Well, that builds what we call a travel time surface. In GIS, it's a whole module in ArcGIS, and it's travel time module. Network analysis, they call it. Well, we're going to play around with that a little bit more in an application setting. And then this idea that once I can measure shortest, doesn't have to be straight anymore, doesn't have to be 2 points, off that surface I can say, well, show me that shortest route that isn't necessarily straight from the headquarters to anywhere in my response district. We'll play around with that a little bit. That's called optimal path routing. And we're going to use that routing as least cost routing in siting a power line, for example. Then we come down here and we have another kind of this distance-related mathematics, and that's three-dimensional geometry, solid geometry. And that has to do with view sheds that we discussed last time. From this location, mark everywhere that would be seen. Splash, and it deals with the tangent as that wavefront moves out to determine whether where it's gray, it's a defilage, where it's red, you could see it. And then we said, well, we could do it for the whole network instead of just 1 point. And then we could say, geez, some of the areas along that road network, some have lots of cars and some have less, so why don't I come up with a weighted visual exposure density surface? How long we've been doing that? Since the 1970s. How long have you been doing that? I'd say haven't started on that path yet for most of you. All right, let's try it. See if we can understand that concept a bit. 2 minutes away. 3 minutes away. Ooh, that was having trouble with the internet, I guess. Wow. All right. I'm not going to be defeated here. I'll go to and run it this way, I hope. There's 1 minute away. Traveling away from headquarters, 2, 3, no, gee, I must have a corrupt file there. Well, let's see how far we get. Now we're back into, no, we're not. Well, this is where we had to end up anyway. Wow. I developed this on 2003 PowerPoint. I wonder if year 2010 doesn't like it. All right, well, what we built last time was this accumulated surface. Farthest away location is 96 minutes away. This is going to work. That's a conceptual space. It's taking our real world, and now the values represent a concept of minutes away by either truck, ATV, or hiking. Well, now we're over here in real space. There's the elevation surface. So let's marry those two together. Why this is so high, it's not saying that's the elevation. Don't keep thinking everything's in an elevation. It's really high because that's way down there in Hellhole along Roaring Fork River that takes you forever to drive all the way down here, as you would have seen, across the bridge is the only way I can do it. You get killed if you try to pass that Roaring Fork by foot, by ATV, or by truck. You got to go to the bridge, so I got to go all the way down here. I got to go all the way up there until I run out of road. Then I get to drive my little ATV up for a while, and then pretty soon I'm walking. That's time. This is dirt. And why? Is I'm having a heck of a time walking down there into Hellhole. All right. See how this? Ah, good. This one kind of worked. So if that's my objective, this is where I'm going to leave. The question is, well, how do I get there? It's not a straight line anymore. I just can't assume that. So you go down this cost surface, it's called. Cost is time. As fast as you can, as steep as you can. And then there's where we're hiking. There's where ATVing. There's where to park your truck. And that's the route along the road network to get there in 96 minutes, which is optimally the shortest. Bunch of ways you could get there, but all of them would be longer. Least cost path analysis. Now we do that a heck of a lot. Instead of being travel time, for example, instead of having friction that you say, oh, it's steep slope, you got to walk really slow there, and there's lots of trees. Rather than that, we can have costs based upon engineering for building an electric transmission line. We can look at legal costs that might be involved, things I have to buy, eminent domain that I have to enter into, land use, I might have to change zoning, political, and a whole bunch of other factors, which in our little map stack, we put together for an overall, do you want to go there with your power line? Is this a good place to put a power line? Oh, good, no, it cost me a fortune to engineer it in there. Oh my God, we'd have to buy the property from Jack Graham or something like that. Over here, oh wow, this would be really easy to build it. No one seems to really care about it if we put a power line there. What about its view? Oh, no one would see it there. That's a great place to build it. So just like the relative ease of travel, building that travel time surface, we have an accumulated cost surface. From a starting point to everywhere, you identify your end point where you want to end up. And when it comes down, it has the optimal cost route for the power line, which no one trusts. What we do all the time is we then ask, well, what's the next best route? Show us the next best and the next best. In fact, show us the top 5% optimal. And that becomes an optimal corridor. Then we go out and pick up trucks and try to figure out exactly where it ought to go. Least cost analysis. How long has that been with us? Actually, people were trying to do this on little yellow sheets of paper in the 30s. Came to fruition in computers in the 70s and 80s. So far, it's not mainstream in GIS. All right, I'll apologize for that. We made it all the way down to here. This one was built in PPTX. All right, there was that idea of an accumulation surface. It happens to be travel time in that case. And then that idea of least cost path. All right, now let's put it in that context. Those kinds of things get natural resource types frothing at the mouth. Oh my God, I could figure out the optimal road network for harvesting half of, I'm Diashawa and I'm up there in British Columbia. And I control crown land that's bigger than the state of Colorado. Problem is, there aren't many roads there. Where would I put my haul roads? Where would I put my secondary roads? Where would I put my jammer roads? I'll tell you, they do a lot of this to figure it out. All right, but we're going to try one with fire. The consequences of wildfire have never been greater because more people are moving into fire-prone areas. Doesn't that sound a bit like Colorado? There's an increasing need for wildfire risk assessment, fuel treatments, mitigation, planning, prevention, awareness, wildfire behavior modeling. I stole this from someone's report. Real-time suppression response and recovery preparedness to reduce risk. Let's look at these two. Well, this little company over here, left out an H. Technoselva. They've got the coolest little thing. Technoselva came out of Leon, Spain. we work with them a lot, and they've since moved their U.S. headquarters to San Diego, because San Diego burns up a lot. Plus they have wealthy people that are willing to pay for this stuff. So it goes, splash, tell me where the fire is. I've got this thing opened up on the hood of my pickup truck. He runs it in an ANIS, I think it's called. It's a tablet computer, right on top of the pickup truck. Initiation, fire initiation. And it sucks in off of Verizon Internet metadata, all of the maps that are necessary from their home base. All that gets sucked into the computer, and then it goes 1 away, 2 away, 3 away, 4 away, where now when it's moving out, again, it's not working in time of hiking. It's working with the fuel conditions, the weather conditions, time of day. Fires heat themselves up uphill, but they don't do it downhill. It's got all this stuff in there about movement of wildfire, but it's analogous to that simple thing we talked about, hiking through the woods. There it is. Fire. I think that's 2.5 hours later. No, that's much more than that. Maybe that's more like 18 hours later. That's where they predict it would be. Well, that's where it'd be if we didn't do anything. That's where this other thing comes in. We're going to have to marry that in. Well, up here we have risk. And one of the risk elements is the probability that there's going to be a fire across any one of our little squares. Then it has to do with the intensity of burn, something called exposure, a hazard, and then susceptibility. All of that's what's called a risk model. Boy, there's all sorts of risk science out there. This one just isn't tuned to wildfire. So if we take that risk and then we look on the assessor's data, that's all available in the United States, downloadable. We know for every square what's there. And if you multiply risk, still a probability, times value, you come up with a dollar exposure. So for this subdivision in San Diego County, it has a $41.47 million exposure if a wildfire approaches it. If I know that, and it's sitting right here, I'll probably try to move some resources over there to keep from burning down those mega estates. That's using GIS technology and spatial thinking. So here's our comparison. Let's try this, spatial statistics, the farmer side. So where do they get into this? They could care less about movements. They could care less about view sheds. That isn't why they got into this technology. They got into it because they're really interested in spatial coincidence, and they want to do things like build prescription maps. They want to do spatial t-tests between two periods. Oh, this side of the field significantly different, but this side isn't. They don't want one number that says your field is or isn't significantly different between two time periods. What does that tell you about managing your field? Nothing. But if it says, yeah, there's a big difference over here. No, there isn't a big difference over there. It immediately says why. And if I can understand that, I'll manage spatially my field. That's what they wanted to do. All right, let's see what they do. But we got to go backwards. We're back there at that old last session. We have traditional statistics. We take a pile of numbers. Let's say we poked holes in the ground, and we got this amount of lead in each one of the returns from the soil lab at each location. We calculate the average, but that really means you're fitting a standard normal density function, and then you're talking about plus or minus 1 standard deviation. Assume everywhere in the project area the same. But what we found out is if we keep track of where we poke those holes in the ground, we'll see some of them are really low and then some of them are really high. And if we look at them in 3D over the project area. You say, wow, all the big stuff's up here, all the little stuff's down here. We throw that away when we do non-spatial statistics. We throw the variance bathwater, baby, out with the bathwater. Go to all that trouble to collect that information. And then we just throw it away and aggregate it over the entire polygon. Well, here's the spatial distribution. Just like this is the numeric distribution. We fit a density function, not a Gaussian standard normal in 2 space, but how about a Krieg in 3 space? Or an IDW in 3 space? Now it all of a sudden says, you know, around in here there's a lot of that lead, but down in here there's hardly any. And then if we put those two together, we can find out where it's unusually high or unusually low. And if it's unusually high or low, that's telling you that side of your project area you ought to do something different than that side. That's the mega technology that's going to change science. All right, one more review. Then we started playing around with this multivariate statistics stuff. Ah, this is cool. Here's 2 maps, but since they're already aligned in space, I now have pairs of numbers for every location. And if I move those pairs of numbers into number space, increasing slope, increasing elevation, I'll find locations that are high elevation and high steep slope. And I'll find some that are low. And I'll find all sorts, looks like a shotgun pattern. That's called a scatter plot in statistics. We take that scatter plot in traditional statistics, cluster it, and then once that clustering is done, I asked for 2 clusters, it breaks it optimally into 2 clusters, kind of the low lows and the high highs. What's great is because every one of those pairs, I know where they came from, I can turn it into a map and find out that my low lows are here and my high highs are there. Didn't do that before in non-spatial statistics. Clustering. Correlation. Well, here's this ugly equation that I'm pretty sure if you ever had a stat course you had to deal with. Probably ended up being a button on your calculator. We can take 2 maps and do 1 solution, or we could move it around and do 625 solutions, stopping at each square, reaching around, grabbing its neighbors, and say, you know, around here, what's the correlation? And around here, what's the correlation? And around here, that creates a correlation map. That is tremendously powerful to a scientist. Problem is, GIS, we haven't communicated very well across campus. They have no idea they could do this. We've told them, great technology to find a pizza parlor when you're on the road. Woo, that's all noisy stuff. All right, let's carry that a little bit further. Now we're into the application. We're into precision agriculture. This is what I meant by digging holes in the ground. So here's an oversampled field up in Brighton area. An SF research project, probably 4 or 5 times as many as a farmer would do. But we were trying to do science, so here's the surface it builds for phosphorus across the field. Wow, a lot over here, I wonder why. Not much over here. Gee, I wonder why. And I wonder if that is going to have any bearing on me making a decision about how to fertilize this field. Well, here they are. Phosphorus, potassium, nitrogen, pH, organic matter, all kinds of stuff they've been using for years in their science to figure out how plants grow, corn or barley. Problem is, a human just can't put this together. Bottom line is, as a human, if you think this GIS is mapping and display, we're missing the boat. You can't see but broad generalized patterns in one map. You certainly can't see They're coincidence. Hence, Precision Ag said, hey, I'm going to use this map analysis stuff. But computers can see detailed numeric patterns in data space. This time my data space isn't just elevation against slope, not 2D, 3D. Nitrogen, phosphorus, potassium, and every one of these little pinpricks over here is now a triplet of data. It's called a tuple in stat and database speak. Plots somewhere in that cube. We can apply the same clustering algorithm. And the way it works, ooh, now we're lifting up and looking underneath the rock of spatial statistics. Well, I bet you'll handle this. It works with data distance, because we're in data space. And data distance is just the Pythagorean theorem. But the Pythagorean theorem expands into 3 space. A squared, what's the difference between the 2 locations, measurements in potassium? A squared. What's the difference in phosphorus? B squared. What's the difference in nitrogen? C squared. Sum them, square root them, and that tells you how far apart they are in this abstract mathematics space. But nothing says we have to stop at 3 space. We do, because we're humans. I can't draw it anymore. But it'll go to n space. Biggest n space I've worked with was 26 data layers. Did that with remote sensing stuff. Channels. If you had a remote sensing course, this is just remote sensing. It's just the numbers are different. They're not reflected light. When was this known? This stuff was all written up in packages in the 70s. Have we applied it in GIS? Not a whole lot. Groups of relatively close, that means their data distances are small, are grouped into data clusters, such that the intra-cluster inside a grouping is as small can be. They're as close as can be. And yet between the different clusters are as far apart as can be, intercluster. And the thing called isodata algorithm, been around since the 60s, it optimizes such that it minimizes the intercluster and maximizes the intercluster, intercluster. Broke our field up into 3 different groupings. Now, I talked about each square being like it was a little tiny field. It's a little too much resolution. So what this does is now say, you know, I'm going to come up with a fertility program, fertilizer I'm going to put on the field, that's optimized, perfect for this pattern, this clusters. And then I'm going to do a different one for this clusters, and I'm going to do a different cluster over there. They just divided their field. Ah, the farmer says, now we're getting somewhere. I divided my field into 3 separate fields so that I could work with them better instead of one petcock setting for the whole field. Well, that's what this does. This is their approach to GIS, analytically. Oh, they love GPS navigation and all those technological tools, just like everybody. But this is their analytical paradigm. Is I've got this thing called a yield map. So when I go through the field, I'm going to note how much I'm cutting. Ooh, lots of grain here. And I'm going to keep track of it using GPS. That becomes a dependent variable. That's the thing I want to predict, I want to deal with, I want to optimize. That guy called a dependent variable. It's a map variable, composed in this case of about 12,000 little squares over the field. poke holes in the ground, lined up in the same stack, we get independent map variables. And if we can put independent map variables and dependent map variables, we can build what's called a prescription map that tells the rig as it moves through the field, put a little more over here, but don't put as much over there, even if the rig is splitting between two things. It does it automatically. Pretty nifty application, pretty advanced, pretty agriculture, but doesn't have a cute little view shed in it. There's nothing in there about consensus building and all those things in natural resources. It's called spatial data mining. So we have a term for it, Wikipedia term, spatial data mining. And in that case, we have dependent and independent variables. A dependent variable that we use a lot in geobusiness is sales. Every time you swipe your card, I know where you live and I know what you bought. That's why you want to be on the reward circuit with Best Buy, for example. I put you like